Three balanced Y connected loads. So here is one load. I'll just go like this. Three of them. If I can fit them there, oh boy. This is going to be fun trying to fit these on one sheet of paper. Let me just, and we'll come back and see what else in each one. Three balanced Y-connected load are installed on a balanced three-phase, four-wire system. Load 1, that's this one, draws a total power of 6 kilowatts. Total 6 kilowatts. That means each one is what? 2 kilowatts. At a unity power factor, that means power factor equals to 1. Load 2, the second one, 10 kVA, 10. That means each one is going to be what, 10 over 3? 10 over 3 kVA. Power factor 0.96 lagging. 0.96, and it's lagging for each one of these. And the third one is what? 7 kilowatts, so 7 divided by 3, that's each one. Kilowatts. 0.85 lagging, the power factor. If the phase voltage at the loads, that's this voltage right here. So remember, these are connected in parallel. That this end is connected to this, connected to that. This end is connected to this, connected to that one. And these ends connected together. The voltage between A and N at the load, that's why capital letters I'm using here, is 135 volts RMS. Now in this problem does not say RMS, but somehow on my book here I wrote RMS on it, so I must have seen it before and I changed it, so they forgot to write RMS on it.
I think for all of them they just assume
It was RMS? Could be. Yep. Now each one of these lines have a resistance of what? 1 ohm. I'm not going to draw all the lines there. And now we got the source here.
I thought it was 1 ohm on the neutral and 0.1 on the.
Is it?
On A.
Each line has a resistance of 0.1. My mistake. Yep. My eye went down. One line. And neutral has a 1 ohm resistance. My eye slipped down one line. And there's a 1 ohm going to actually be here, or 0.1, not 1. Find the total power drawn by the load, the combined power factor, total power loss on the line, and the voltage source VAN, and the power factor of the source. Lots of stuff. Okay, no big deal. Well, the circuit looks like a mess. You can see just by looking at it. It's a nightmare. So what you want to do, look at per phase, like this one, or that one. So if you look at it per phase, this way, actually, let's go on the next page, make it nice and clean. If you look at one phase alone, this is what my source looks like. This is A. and this is N. This is the 0.1 ohm, and this is the first one, the first load. And this is the one here. The first one has 2 kilowatts, 2,000 watts. Power factor equals to 1. There is no leading or lagging when the power factor is 1. The next load, this is A, and this is N. The next one, 10 over 3. What's 10 over 3? 3,333, is it? VA. That's your complex power. Power factor is what? 0.96. And what? Lagging. And the last one, seven divided by 3. Is that 2,333, is it? Kilowatts. Power factor 0.85, lagging. And the only other thing I know is the voltage right here, with the plus on the here and the minus down here. This is 135 volts RMS.
Wouldn't that be before the resistor or not?
Before the resistor. That's the line. That's the load. So the VAN, it says the load voltage here. So that's the voltage, then notice what I drew between A and N. That's the line, that's a different, once I know the line, then I know what VAN here, little VAN. That's one of the questions, I think the fourth, fifth question back, what is that voltage of the source? And this becomes like one of the old problems we had before. We can look at each one, calculate the current going through them. We'll call this I sub 1, I sub 2, I sub 3. You can use complex power or anything you want to use.
So, how did you make that circuit, sir? I missed that.
One phase. You trace.
All the A's.
Yep.
Are you going through a loop?
Yes. Let me draw with pink here, or a different color. Blue. I don't know what happened to my pink marker. I'll use the blue. That's going through this.
So we're just going down all the A paths and then
Yep.
on the neutral.
Yep. That's one loop. Notice they all just looks like crooked there. I just made them straight line.
So what do you do if there's no neutral? You just go all the way around?
You can. So that's what I have here. Now let's calculate this. We know actually that's the real power. The imaginary is 0. So if you want to find your complex power for the first one, is going to be what? 2,000 plus J0. Power factor is 1. That means the angle is 0 degree. There is no imaginary. That's for this one. I know what I sub 1 is. We know S1 equals what? 135 angle 0. That's the voltage, times I sub 1 conjugate. And we know that's equal what? To 2,000 plus J0. Can you find I sub 1 conjugate? There's my calculator right here. Let me just make sure I'm actually in mode, F3 mode, F1 mode, no, F3 is mode, I think. Oh no, mode is mode on this calculator, I forgot, mode. Polar, good. So that'll be what, 2,000, clear, escape, here we go, 2,000, is it 2,000? Yeah, divided by 135 angle 0. And it's 14.8 angle 0. What's I sub 1 then? 14.8 angle?
Negative 0.
Still negative 0, which is still 0. So that's I sub 1. We need that. Now, let's find I sub 2. What do we know here is the complex power. So let's look at source 2 here. Again, if I draw a picture of it, what I have is the complex power. It says VA. VA are the units for the complex power. So I know it's lagging, so the angle is positive. So I know this value is 3,333. And I know what this angle is. What's this angle? Inverse cosine of what? 0.96. $16 degrees, roughly. 16.2 degrees. Can I find this side and that side? We'll call them X and Y. So this is going to be complex power for 2 is going to be 3,333 cosine 16 degrees plus J 3,333 sine 16 degrees. Finding the X and Y component, that's all you're doing. 3,333 cosine cosine 16 degrees. So that's roughly 32,000. Few changes here. Plus J 3,333.
How could it be like 10 times higher than
3,200, not 32,000. Yeah. 3,200 plus J, that'll be the sine here. And that's about 920, 919. So I can find now what I sub 2. Again, 3,200 plus J920 equals VRMS, which is 135 angle 0, and I sub 2 conjugate. That tells me I sub 2 conjugate, it will be what? Let me go to my calculator here. F1, 8, let me clear everything. Here we go. Parentheses, 3,200 plus 920J divided by 135, angle 0, is 24.7 angle 16 degrees. So what is I sub 2 now?
negative 16 degrees?
Yep. 24.7 angle negative 16 degrees. And we found I sub 2 now. Check. Let's look at I sub 3. So now I'm going to do source 3, or S3. For that one, you are given the real value, kilowatts. you are given this number, 233, I'll say 0, round it to 2330, that's plenty. There's no kilo, I already changed it to watts here, right? There's no K here. I already converted that. It was 2.3 kilowatts or 2,000 watts. So roughly 2330, roughly. We know what this angle is, the inverse cosine of 0.85, and it's lagging, so we know it's positive. So here we go. Inverse cosine 0.85, almost 32 degrees, 31.778. Can I find that side? Sure. Tangent 32 degrees equals the side that's opposite over the adjacent. So 2330 times the tangent of 32 degrees. I got roughly 1460, roughly. 56, 57, so I'll go 60. So now I know what S3 is. It's 2330 plus J1460. Can I find I sub 3? Sure. Equals VRMS, and that's what, 135 angle 0 times I sub 3 conjugate, which tells me I sub 3 conjugate equals to what? Parentheses 2330 plus 1460J divided by 135, 20.4 angle 32 degrees. So I sub 3 will be what? 20.4 angle negative 32 degrees. So I know I1, I2, and I3. Can I find what I is going to the load? Which is what? The sum of them? I sub 1 plus I sub 2 plus I sub 3. What is I sub 1? 14.8 angle 0. I2 is what? 24.7 angle negative 16. And 3 will be what? 20.4 angle negative 32. So I take my fancy calculator here, put them all in, and see what they answer. 24.7 angle negative 16 plus 20.4 angle negative 32. According to my calculator, it's 58.6 angle negative 17.5. I'll go negative 18 degrees. I think the first question they ask us for that one, what is the total power drawn by the load? If they're looking for the average power, we know what the average power drawn by the load. We know what each one is. So how much by the first one? The first one, we know what the average power here was 2,000, the real power. For the second one, we know what that number. So the first one was what? 2,000, that's the average power. The second one was what? 3,200, that's the average power, the real power. And the last one is 2,330. So if you add them, 2,000 and 3,000 is what? 5,200, 52, 7.5 maybe? That's for one phase. 7.5. You get how many phases there? 3. So the total power three times the sum of them, which is the 2,000, plus the 2,330, plus what was the next one? I missed one. 3,200, right? So add these three, multiply them by 3. You have 3 sets of them. 2,000 plus 2,330 plus 3,200, multiply it by 3, and it's roughly 22,600 watts, which is what? 22.6 kilowatts. Is that one of the answers?
Yes.
Yep, that's the first one. The second question. Second question is the combined power factor of the load. That's question 1. Question 2, combined power factor of the load. Where is it? Is that what they're looking for? Yep, of the loads. Well, we know actually what, you look at this is the whole load, or the combined loads, right here. We know what the voltage, we know what the current. Power factor is going to be what? Cosine theta V minus theta I. Theta V for that one is 0 for the combined loads. The voltage here is 0 minus the current. What is the combined current? We just did that. Is it negative 18? So minus a minus, that's plus 18. The fact the angle is positive, that tells me it's lagging. So what's cosine 18 degrees? Cosine of 18 degrees. And it's 0.95 lagging. Was that a correct answer there? 0.954 lagging, yes. Another question. How much power lost in the lines? Well, let's look at the lines. Let me go back to the first picture I drew there. There's a 0.1 here. So there's power loss. There's a 0.1 here. There's power loss. There's a 0.1 here. There's power loss. And there's one 1 ohm resistor. Only one. There's 3 of these. And there's 1 of these. Let's find out how much power lost through one of these. Then multiply it by 3 to find the total of them. Find the power lost here. And add them, and that's the power lost by the line. Everyone see that? So let's see. Remember, these are resistors, so it's only real power. Average power lost by the 0.1 ohm resistor. Again, these are RMS value. So it's VRMS, IRMS times what? Well, the phase shift is going to be 0.
So times 1.
So because cosine, it is cosine, theta V minus theta I, but theta V minus theta I is going to be a 0 phase shift here. So it's really going to be VRMS, IRMS. When I say VRMS, it's VRMS of this guy, the 0.1. Well, I don't know what that is, but I know the current. Ohm's law says what? V equals I times R. So that's going to be what? 0.1 times I RMS. Oh, I don't know why I put asterisk, not conjugate, I meant to say square. And I wrote asterisk there. And the phase shift is going to be 0. So this is going to be for the 0.1. Where's the current? I have it somewhere. The current going through that 58.6. So it's going to be 0.1 times 58.6 squared. And I should have put the square outside. Boy, these early classes. Doesn't really matter. I can put inside, outside, but that's so 58.6 squared times 0.1 is what? So that's equal to 343.4 roughly watts. Well, how many 0.1 we have there? How many of these resistors? 3 of them. So what is 3 times 0.1? 3, not 0.1, 3 times the value through, the power through 0.1. P of 0.1. That's 3 times 343.4. Oh, I get a syntax error, or I did the multiplication twice. Okay, 3 times. And 1,030. Watts.
What about the 1 ohm resistor?
Oh, that's a good question.
Isn't it neutral? Isn't it
What do you think the current going through it?
0?
Yes. Why? Look at that one. Just take any phase. If you know what this current coming down, which we know what that is, that was I, right? And what was that value there?
58 angle negative 18.
58.4 angle, what negative?
18.
Negative, was negative 18? Okay. What do you think the current going through this one? That's the B here. This is going to be 58.4, because it's balanced. Subtract 120 from that. What's minus 18 minus 120? Negative 138. Here's C. What do you think this current here? 58.4. Subtract another 120 out of this. Is that 258? So you got this current, it's balanced. You got this current coming, you got that current going. Where are they going to go? That's this current. And there's the 1 ohm resistor. Let's find out what I is for this one. Well, that's what? KCL. Sum of the current entering the node equals sum of the current leaving that node. So I will have to be 58.4 angle negative 18 plus 58.4 angle negative 138 plus 58.4 angle negative 258. And let's add them all and see what that current is. Here's my calculator. I'll put it there so you get to see it. 58.4, what was the first one? Angle what? 18? Negative 18. Plus 58.4 angle what? Negative 138 plus 58.4. Oh, I gotta use brackets. 58.4 angle. Ooh. Oh. Angle. What was it? Negative 258. Ready to see what the answer is? What do you got for an answer?
0.
0. 0.000000000000001 angle 90 degrees. That's a 0. So I is 0. If I is 0, what is the average power by the 1 ohm resistor? It's 1 times 0 squared, and that's a 0. So here we go. The total power lost in the lines will equal to what? 1030 watts. So the 1 ohm does nothing, because that current coming out of this should be 0.
So when one supply is supplying current to the network, another one's taking it away?
Well, you have to picture this like your ground, just going to the ground, it's not coming back. Yes, so this one's supplying, and it's just going to the ground and coming back, you know. Yes.
So neutral is going to be 0 only if it's a balanced.
Well, if this is not balanced, if these angles are not, that's correct. They will not add up to a 0. Imagine if this was angle 15 and this angle 17. If I just change one of these numbers, notice if I go there, let me go back to that equation. Oh, not there, clear. Let me go back to this one. And I just changed one of those angles. The question, what about if it's not balanced? If it's not balanced, like this angle is not really negative 250. Let's say this angle was we have a negative there, so that's 2 negative. Negative 74, just put a different value. And this angle was plus 38. It's not a balanced one. Once you hit enter, it's no longer a 0. So when you have a balanced system, that sum of the current coming through this is going to be a 0.
So then in a balanced system, the neutral line doesn't really have a role?
Ground. Yeah.
Is it always 0?
If it's balanced, better be. Yeah. If you have a balanced source, and a balanced load, it should be 0. If the source is not balanced, this could be balanced, but if the source is not balanced, then it's not. Because the voltage is no longer, 120 degrees, so you got to go through the math, every one of them, piece by piece, and see what the value there.
Are we going to do anything with unbalanced? Or
Maybe. I was looking actually for one, so I might pick one shortly if we have time. Yeah, we might have some time. There's a couple more questions left here. What was it?
Phase voltage.
The phase voltage of the source. What is the source? Well, we know what the phase voltage of the source. We know what VAN is going to be. Go back to this picture. Not this one. Where'd you go? A lot of sheets now. If I know, just look right here. You know what the voltage here, so VAN is going to be what? Is the voltage drop right here, which is what? 0.1 times the current through it. And what's the current through it? What was I? 58.6 angle negative 18. That's the voltage drop right here. Plus, add to it this voltage here, which is what? 135 angle 0. It's this voltage right there. Add to it the drop. We know this current is 0 here. We just did that. There's nothing here. So 0.1 times that. Oh, wait a minute. Uh-oh. Nope. Nope. Okay. Look at this. Multiply the numbers. 0.1 times. Well, actually, end up with 5.5 5.86, clear everything, F18, clear everything. Ooh, F18, get out. If you do 0.1 times 58.6 angle negative 18 plus 135 angle 0, you end up with 140 point what? 6 angle almost a 0. Can you see it? Angle what? Negative 0.7 volts. So really, you're probably going to write that 140.6, either negative 1 or 0 degree. That's what the voltage is going to be.
Why do we add 35 again?
Huh?
Why do we add 35?
135.
If that's not angle negative 18, how is the power to the 1.1 resistor?
That's this current, right? Isn't that the current? Negative 18, 58.1, negative 18?
The source voltage isn't the same angle. How does that?
No, I'm looking for that.
Oh,
I'm looking for that value. So that's why it's negative 1. So we know what the current going through this, so there's a voltage drop here plus to minus. And what's the value of that? It's 0.1 times I. So I know what I is. You multiply it by 0.1, and that will give you that value. Then add to it the 135. So if they're looking for the magnitude of that, because that means VBN, if you want to find VBN now in VCN, is going to be 140.6 angle subtract 120, negative 121, and VCN will be 140.6 subtract another, will be negative 241 degrees. But I think they're looking for just the magnitude of that here. What is VAN? Does it say magnitude? What is the question?
Which question?
The phase voltage at the source. Now the last one,
Voltage per
yep,
phase.
yep. But I think they were looking, it doesn't say the magnitude, because if they're looking for the angle, then you go negative 1, negative 121, negative 240, but what they're looking for is 140.6. That's the magnitude.
What I did was negative VAN plus the currents plus the VA plus the 135
Yeah,
equals 0.
yeah, that's the same thing.
And I got 140.6?
Angle negative 1 degrees.
Yes.
Yeah. But they're not putting the negative 1. I'm just looking at the solution. They're just giving you the magnitude. So I think they meant, that's what I'm saying, I think they meant just give me the magnitude of that. But there's the full answer. You want the magnitude, is 140.6. You want the angle, there's the angle for each one. And the last piece, the power factor at which the source is operating. Well, the power factor of the source it's cosine theta v minus theta I. And that's, I wish I carried more decimal places. This will be cosine. We know what theta v here is, negative 1 degree.
Exactly, it's negative 0.72, and then the other one's negative 17.5.
0.72 minus 0.72. What was the other one?
17 point.
Negative, right?
Yeah, so
So it'll be plus 17.5, you said?
5.3.
5.3. So, because I was rounding the numbers, so if you carry all the digits, that'll be cosine, and notice it's positive angle. So 17.53 minus 0.72 is 16.8. It really won't make a difference if I use 18 and 1. It's not going to make that much of a difference. And what's the cosine of that? Cosine of 16.81, 0.5957, and it's lagging. And if I did actually the 17, if I use 18 and 1, that would be 17. How much of a difference will that answer? Will be 0.9563 instead of 7. You know, so a little hair just off there. And what do they have here? 957 lagging. Yep. What made this problem not bad, actually, I won't say easy, but I say not bad, because it was Y and Y. A lot of times, they're not really Y and Y. It's Y to delta and delta to Y, and you have to convert. Couple of questions came up during this problem, and I'll see if I can find one where we don't have a balanced source. We're still Y to Y, but we don't have a balanced source or a balanced load. Let me see if I can find one quickly. My machine died on me, so I just got to reload this one.
Unlucky.
I hate dead silent on the camera there, but just gotta look for one quickly. Let's see. I don't know what chapter even we are in this one.
At least that's what 3 phases.
No, not this one. Okay, let's try this one. No. Maybe I'll find something. Maybe, maybe not. Not this one. I'm trying to find something. Ooh. Well, this is not actually. Maybe I'll jump to that because I can't find one off the top of my head quickly. I'll try to think of one next time. I don't want to just keep the camera running. But let's take this example. Change the story a little bit because that takes us to where I need to go next. Here's what we have. We have a balanced three-phase system. The source is a balanced Y source, ABC, balanced ABC. ABC, that means angle B is negative 120, angle C is negative 240. Remember that? If it's balanced, it's ABC. If it's CBA, we add the 120. So here's what we know. We know we have a Y source. But what I'm going to give you here is VAB, which is 208 angle 60 degrees. Volts RMS.
208 or 20.8?
208, 208, angle 60. Now is attached to a Y load of each one is 8 plus J5. Bless you. in parallel with a balanced delta load. Delta load.
In parallel, you said?
Yep. So this is A, this is A, this is A. With these delta load, each one is 21 plus J12. Plus J12. So basically you have this attached to this, attached to that one. Now that creates a problem for us.
Can we just change the delta to a Y?
Well, that's what we have to do. Yep. And I forgot to add, in addition to that, let's add a line impedance here. A line impedance of 1.2 plus J1. This is 1.2 ohm plus J1. Find the phase current. So I need to find what is I sub A to A. What is that current?
What's the difference between phase current and line current?
Well, phase current, you go on like from here to there. It's the same thing with the phase voltage. Phase voltage is VAN. Line voltage is VAB. That's known as line voltage. In this case, that current going through this is the same current going through that. Yeah. The problem here is I got that delta. And I got to look at my notes from last semester because I don't have them. I usually throw that sheet of paper somewhere here from delta to Y, Y to delta. And I hope I have it somewhere here. Oh, what do you know? This is from last semester. This is when actually we dealt with resistors only. Remember that?
Isn't it basically the same thing though?
Well, it's going to be the same except instead of R, we're going to say Z1, Z2, and Z3. But it's going to make the math a little bit easier.
This is?
This section, because it's balanced. If it's balanced, what happens? These values are the same. If they are the same, what are you going to have here?
Products over sum.
So it'll be 3 times. So this would be like, yep. So let's derive this. So if you have, let's say Z here, we'll call it Z delta. Z delta. Z delta. And you want to convert that to the Y value. ZY, ZY, and ZY. That's Y, not V. So ZY, based on my equation from last semester, from circuits 1, he used to say multiply this times that. So Z delta times Z delta over the sum of them, which is Z delta plus Z delta plus Z delta. What are you going to have? 3Z delta. And what do you notice about them? It becomes Z delta over what? 3. If it's balanced. If it's not, then you're going to go Z1 times Z2 in the bottom. I mean on the top, Z1 times Z2 in the bottom, Z1 plus Z2 plus Z3. And do it the long way. But if it's balanced, it makes the math easy. To do the reverse here, Z delta, if you want to find Z delta, if you know the Y values, here's the equation for that. So it says multiply ZY times ZY plus ZY times ZY. This times this, plus this times this, plus this times this. There's 3 sets of them. Over what? If I'm looking for this, I gotta divide it by that one, which is zy. And what do you notice quickly? Z delta equals, well, just basic math here, is 3 times zy. Or zy equals z delta over 3. Again, that's assuming it's balanced. If it's not balanced, we're going to redo everything. So now you look at your circuit, and this is what we have for a circuit. I can convert this to a y now by dividing it by 3. Right? Zy equals z delta over 3. Yes, 7 plus 4j. So I will have this. Here's the first one. I'm only focusing on one branch, really. I'm making that big. So this one's 8 plus 5j. And when you convert the delta to y, you divide by 3, and you're going to have what? 7 plus 4j.
Can you add those, like?
I can. Product over the sum. They're in parallel.
Can you add those two y's?
I could, sure.
Should we do that, or is that not really?
Doesn't matter if you want to or not, because if you look at one branch now, oh, I forgot to put it on the top, which is what?
1.2 plus j.
1 plus 2,
1.2.
oh, 1.2 plus 1j. I'll go like this. So if I look at one loop there, that's all I'm interested in. That's your circuit. So you might have an ugly one, but if you do a little quick conversion, it's not bad. So you have VAN.
We actually have VAB.
Now we're going to find what VAN, but that's called VAN. We'll find it in a second. We have 1.2 plus 1j. You have 8 plus 5j. And if you want to combine these into one, go ahead. If you don't like to have them as separate ones, you want to combine them, go ahead. I forgot to tell you, what was the question? Finding what is A to N. Yeah, since I'm looking for this current going from here to there, if you want to combine these, product over the sum, be my guest. Doesn't change anything. So if you want to combine them, that will make it what? VAN 1.2 plus 1j. And now let's combine these. The product over the sum. I'll go to my calculator here.
I got 3.7 plus 2.2i.
3.7 plus 2.2i or j. Luke said he got, I didn't do it, Luke said he got 3.7 plus 2.2j. Is that good? Product over the sum?
Yeah, I got the same.
Same thing, good. You want to change it to phasor? It's probably somewhere around like 4, 4.4, 4.3, about 4.3. And that's almost a half. The angle about, you know what, the angle is going to be close to 30 degrees.
You are exactly right.
Do what?
What is it?
It's 4.3 angle 30.7.
Yeah. 30 point, that's good.
Why is that
30.7.
like a good thing?
No, I just said 30.7, I said good. Well, I guessed it, because this is almost half that number, right? So 2.2 over 3.7, well, almost half, so I figured the angle somewhere around 30 degrees. So it was 31 degrees, 30.8, you know. So if you want to convert that to, I was just guessing to see what the value there. You want to find this current? Well, we don't know what VAN. We know what VAB. That's the line voltage. What was the line voltage there, VAB? In this problem, how big was it?
208.
208, angle 60 degrees. So you know what VAN now. You take the 208 and what do you do with it? Divide it by the square root of 3. And you subtract what from that angle? 30 degrees. That should be 120 because that's a common number. 30 degrees.
120.1.
Yep. That's VAN. So can I find I from A to A? Sure. It's VAN divided by the sum of these. 3.7, 1.2 is a 4.9 plus J 3.2. So 120 angle 30 over 4.9 plus J 3.2.
20 angle negative, 20.5 angle negative 3.1.
20.5 angle, what'd you say?
Negative 3.1.
3.1. That's VAN. I mean I sub AN, not VAN. That's I sub AN. Now if you want to find the current through the phase here from A to N, that's different. So if the question, I forgot if the question when I ask a per phase, find the load, find the current through the load I was looking for. So if you want to find I sub AN,
Shouldn't it be the same current?
same thing for this case. Yep. If you're looking for the combined load, if it's different loads, that's a different story. But if you're looking for the combined load, it's the same. If you're looking for each load, that's a different story. Because that means I need to do what? If I'm looking for each one of these, I gotta find actually, I can do current division, yes. I can do current division, or I can find the voltage here, and the voltage divided by that resistor. Don't even remember what I asked for this.
I think you were asking for VAN.
If I want to find VAN, capital AN, we know what the current is, and we know what the impedance. So VAN is going to be what? 20.5 angle negative 3.1 degree, that's the current, Ohm's law, times that impedance, which is what? 4.3 angle 30 degrees. And that will give me the current, I mean the voltage between A and N. That's the load. VAN, that's the source here, and V capital AN, that's the load. And whatever that number is. Oh, I was about to look for another one, but I'm looking at the clock and it's that time. So that's what I'll do if I have delta and Y. I'll try to change them to match. Make it easy. If the source is delta, I'll make the load delta. If the source is Y, I'll make the loads Y. It's easier to have them matching. If they're not matching, then we got a problem. How do you convert a source from delta to Y? That's how we do it. If you know VAB, you can find VAN. If you know VAN, you can find VAB. If you remember from last time, we said if you have VAN equals some peak value, angle theta, and it's ABC, so ABC positive. That means VAB is going to be what? You take the square root of 3, you multiply it by the peak value, and whatever that theta, you add 30 degrees to it. To do the reverse, to go from VAB to VBN, we'll call it Vmax here, angle phi. Then to find VAN, you divide by the square root of 3. And you subtract 30 degrees. You can change from VAN to VAB. That's really going from Y to delta, delta to Y. Here we go. Our book actually does a full page on conversion here. If you have a Y connected load here, and it's balanced, notice each one has a positive sequence because VBN is negative 120, negative 240. So if you want to find VAB, you multiply it by the square root of 3 and you add 30 degrees to the angle. And once you have VAB, you can find VBC and you can find VCA. How? Subtract 120, subtract 120, I'll give you the next set of values. You can find the current is the same. The line current, I sub A to A, I sub A to N. If you have a delta, and you know VAB, if you want to convert that to VAN, sure enough, they're going to tell you, what is it? They don't actually do that. They don't convert that for you. But you divide it by the square root of 3, and you subtract 30 degrees from it. That's just if you know the load, VAB, you want to find VAN. So let's assume we have this value. So you want to find VBC. Well, it's the same thing. You subtract 120, you subtract another 120 from it. There's no calculation here. If you know VAB, you want to find VBC and VC again. Subtract 120, subtract 120, subtract 120. So I'll stop the video.